Okay, welcome back. Today we're going to be doing our third lecture on compactness. We've talked a bit about what compactness means and why it's such an important concept, but we haven't yet shown beyond a finite set and the other sets that are compact. Okay, finite sets are compact, but today we're actually going to prove that in fact, the interval is compact, the closed interval. And then we're going to show, in fact, that if you're talking about points in R or Rn, that closed and bounded sets are compact. And that's the Heine-Borel theorem. And we'll prove some other theorems about compactness as well. Okay, so I just want to remind you what we've done up until now in terms of what we know about compactness. So from last time, or even the time before, we showed that compact sets are bounded. We also, last time, showed that compact sets are closed. This is true in any metric space. Okay, the proofs we had, if you recall, worked in any metric space. To show compact sets are bounded, does anybody remember the idea? So when you recall key theorems from this course or any math course, you should try to have in your mind a picture of why it's true. Why is it true that compact sets are bounded? Let's see. Well, the idea is to show that the compact set's contained in some ball, right? What ball did we place a compact set in if you know that every cover has a finite subcover? Yes. Good. Take balls of radius 1, and then?
And then you can look at the maximum distance between two balls, and then that neighborhood will contain a point with that radius will contain.
Okay. Now, I'm a little concerned about taking maximum radius between centers of any two balls unless you have how many balls? Finitely many. How do we know there are finitely many balls? Compactness gives us a finite subcover of the cover of all balls with radius 1. Yes? Then we can take a maximum because there are only finitely many things to check. In fact, just take one center and look at the maximum distance to any other center, and then add 2 to account for the balls around, right? That's the picture you have in your head. Compact sets are bounded. And we used finiteness in a very essential way here, right? Which shouldn't surprise us because that's the whole point of compact sets. Compact sets are the next best thing to being finite. Okay, good. Compact sets are closed. What was the picture proof there? Take a compact set, take a point not in the set, and show that that point is what? Not a limit point, which is the same as showing that it has a ball around it that separates it from this compact set. Yes? Good. How did we find this ball? Take a point in the set. And this point.
Yes. And that point and the distance between them, we know that they're separated by 2 balls.
Okay. So there are partner sets for every point in the set and this point.
Right.
Good.
And then you know that.
You have a bunch of partner sets.
Right. And then you know that because it's an open cover of the balls over here, yes, then there's a finite subcover of those.
That cover this. Okay, good. So there, the set of all such partner sets, the sets on the left here, all cover this set. That's a cover. Because this is compact, there exists a finite subcover, and then look at those partners, and there are only finitely many of them, take their intersection. Excellent. That's the picture proof you should have in your head. Okay, awesome. Something else we showed is that closed subsets of compact sets are compact. And we also showed at the very end a result that isn't a result about compactness. It's just a theorem that we'll need, in fact, today that says that if you have nested closed intervals in the real line, then their intersection is actually non-empty. Okay? It's not true for all closed sets, is it? This is a statement about closed intervals. Why is it not true for all closed sets that the intersection is non-empty? Nested closed sets. What if I had closed rays going from 0 to the right, 1 to the right, 2 to the right, 3 to the right? Are those nested? Yeah, they're nested. Is their intersection have anything in it? No. Right? If you take rays that go from 0 all the way to infinity, 1, infinity, 2, infinity, 3, infinity, is there any point that's in all those sets? No. Right? Yes, infinity not being a point, but just the ray that goes off infinitely far. Yes, so the fact that it's this statement is not true for arbitrary closed sets, but it is true for closed intervals. Okay, at the very end of last time I showed you kind of as an aside a cute proof that R is uncountable using this fact. Okay, so today what I would like to do is then begin by showing you, we're going to use this theorem to help us show the first important theorem for today, which is the fact that any closed interval AB is compact. Hooray, this will give us, hopefully, our first large class of sets that are known to be compact in the real line. This is a subset of the real line. That goes without saying, but I will say it anyways. Okay. In general, this is actually true also for K cells in RK. So a K cell, recall, is basically products of closed intervals. They're the rectangular boxes in RK. Okay. Okay. So let's prove this. How are we going to prove that AB is compact, the closed interval AB? How are we going to do this? Let's draw ourselves a little picture. Here's an interval, AB. Well, to show that it's compact, I'd want to show that any open cover has a finite subcover. Now, that's a lot of open covers to check, right? And certainly I could maybe try to start that way. But here's another strategy for proving that this is compact. I could try to prove this by contradiction. How would I start off a proof by contradiction? Good. So suppose not. Suppose AB were not compact. That would mean, instead of every open cover as a finite subcover, that would mean there is an open cover that has no finite subcover. Okay, then there exists an open cover, and let's give it a name. How about G sub alpha? That has no finite subcover. Oh. Now, the nice thing about starting this way is that I now have a specific cover to hang my hat on, right? I can work with this one specific cover and try to show things about it, hopefully get a contradiction. Okay? So, who knows? I don't know what this set looks like, but let me just draw an example cover. Maybe such a cover, consists of sets that look like, there's a bunch of sets here, possibly lots of them. But just pretend for a second that this is my cover. Obviously an infinite cover that has no finite subcover that will cover AB. You with me? We're going to try to get a contradiction. Okay? So, and I'm going to use the nested interval theorem to help here. And the idea is, Well, let's see. The idea is, if this is true, that this cover has no finite subcover for AB, would you agree that it's also true for any subset of this, sub-interval of this set? Would you agree it's also true? That is, if I divided this interval in half, call this point C, maybe C1, would you agree that this cover covers both halves? Yes? Why would it have to be the case that at least one of these halves also has no finite subcover of this red cover? Yes?
Because if both halves had a finite subcover, then we take the union of those finite subcovers and have finite subcover.
Excellent. Everybody happy with that statement? That is, if both halves had a finite subcover for this cover, you just union those two collections and you'd have a subcover of the whole interval. Would you agree? Yes? So, oh, great, I have an interval. What's the next? What do you think I'm going to do next? And while you're thinking about that, let's write down what we've just said. So then, G alpha covers both AC1 and C1b. Everybody agree with that? And the claim is that at least one of which, maybe both, but at least one has no finite subcover. I'm just going to start abbreviating finite subcover if you don't mind. I'm just going to write FS now because I might have to say that again. Okay, at least one has no finite subcover. Which one? Well, I don't care, but say one of them. Let's say it's I1. Let's call it I1. Interval 1. All right. What do you think I'm going to do next? Suppose it's this one. Bonnie? Ooh, split it again. Let's split it exactly in half. Let's call it the next one C2. The next halfway point. Okay? I didn't say that here, but what I'm saying is choose the CI so they always split halfway. Okay, call it I1. Great. Without loss of generality, suppose it's AC1. That's the I1 is. So without loss of generality, this is shorthand. If you're writing it out, you'd write without loss of generality. Let's say I1 is the first interval, just to be explicit, AC1. Let's say that has no finite subcover. Okay, well then let's subdivide again. I'm going to say it halfway using C2, which is the halfway point. And once again, we'll note that, now what are the two halves, Bonnie? AC2 or C2, C1. Note that this or this, one of them, has at least, so note, at least, okay, one of this has no finite subcover. Excellent. Now what? Subdivide again. Thank you. Lindsay's saying subdivide again. So I'm just going to say here continue. And we'll obtain a sequence. I1 contains I2, contains I3, etc. Yes? Of nested closed intervals. And what else is true about this nested set of closed intervals? They're doing what? Oh, they all what? Oh, okay. Well, we're about to, yeah, we're going to use that in just a sec. But what can I say about these intervals besides the fact that they're nested and closed? None of them has a finite subcover. Agreed? for that original red cover. Not only does that, none of them have a finite subcover, but the other thing is I've chosen them so they're always getting smaller and smaller, right? They're always decreasing by half each time. So I'm going to make those two observations. Each halved at each step, and with no finite subcover of the G alphas. Okay, so since I'm gonna refer to this, I'm gonna call this property Cyclops smiley and this double smiley. Okay, these are important properties we're gonna refer to again. But now I have a sequence of nested closed intervals, and so Maya's thinking, oh, I could use this fact, which we conveniently proved last time. And Jacob is saying, this means that these nested closed intervals, what? Good, so there exists a point in all of them. Great. So by the nested interval theorem, there exists, let's call this point, I don't know, why don't we call it x? There exists x in an IN for all n. There's a point in all the sets. All right, so let's just draw a picture here. This was our first interval. This was our second interval. Maybe this is our third. Maybe this is our fourth. Maybe this is our fifth. Each time you're picking one of the two halves at every step. Would you agree that this, because of this theorem, would you agree that there is a point in all the sets? Maybe this point x lies somewhere here. Yes? Do we have a contradiction yet? Not yet. So what? I have a point that's in all the sets. So what? Emil? Look, yes, this point is, this single point is somewhere on this interval. Would you agree it's in some open set of the cover? Maybe it's in this one. Let's make this one special. This one is going to be kind of a brighter red here. This point is in one of these open sets. Yes? Okay. So then what? Think ahead as to where's our contradiction coming. X is in some. Let's call this the special element G alpha. Let's say some G alpha hat of the cover. Okay, so what? X is in one of these open sets. Why is that going to contradict anything about our nested intervals? Jenny? Oh, yes. X is in an open set. So X is an interior point of this set, yes? Therefore, there is, in fact, an interval around X that's still within this element, G sub alpha hat, right? Okay, but why does that say anything? So let's say, so I'm going to mention that this is open. So there exists an R bigger than 0 such that a neighborhood of R around X is completely contained in what? G alpha hat. Help. I agree. There is a neighborhood around this point. You don't mind, I'll make this a green set. This green set is a neighborhood around X that's within the bright red set. Help. Why does that contradict anything about our construction? Someone I haven't heard from yet. Why does this contradict anything about our construction? Thoughts? John, any thoughts? Apparently not. Any thoughts here? Maya? Excellent. Why? This red set is going to be a finite, in fact, not just a finite subcover, but it by itself, a single element, will cover one of these intervals. Which one? Will it cover this first one? Second one? Yeah, in fact, because I'm having these at every stage, would you agree eventually these intervals get so small that they'll live inside the green set and therefore inside the big bright red set? Excellent. That's our contradiction. So there exists in R a radius around this point that's within G sub alpha by Cyclops Smiley. Some I sub n is completely contained in n sub r of x. Meaning what? Well, this means that a single G sub alpha hat covers In, which contradicts what? Double Smiley. And we're in good shape. Okay? Very, very nice argument to show that AB is compact. It's actually, surprisingly non-trivial to show that this one creature is compact. Okay? But it's going to give us a lot of other things as a relatively easy consequence. Okay? We're about to see that. Any questions about this proof? Yes, Willie? Uh-huh. Excellent question. Willie's question was, what if these were open, this was an open interval? What would fail in this proof to show that the open interval is compact, which we know it's not? Hint? This closed interval is just like the open interval except the endpoints, right? So what could happen? Excellent. The intersection of these blue sets could be one of the endpoints, and that's the case where you'll have problems with this argument. Okay? Wonderful question. Other questions about this proof? It takes a second to step back and think about why this is true. So I strongly encourage you to go back and review this proof idea. Okay? This picture says a lot. Okay? Yes, Laura? Excellent question. Laura's question was, would this be sufficient? This kind of argument be sufficient for your writing? So we are getting to the point in the class now where you're beginning to be more and more mature, and you're assuming more and more mature things about your reader. And so I would say it would be, if you're going to write a proof, this is the first approximation. Right? And if you felt like your audience would not understand the halving argument, you might put a little, asterisk and demonstrate that. But if you're writing to somebody who's, 2 weeks behind you in the course, I think this is pretty good. This has all the basic ideas that you want. Okay. I mean, you can stop being, technical, right? At this point in the class, you can stop saying by the commutative or associative property of addition, right? Which I noticed many of you are still doing on your exam. Unless, one of those properties is really the crux, right? But what's the critical idea here? It's not in the little detail, right? But I think, I don't know, let me ask you, would you be happy with this kind of argument if you were the reader? Does somebody need to show that if you have something eventually, it will get within a certain radius? I guess if the answer to that for you is yes, then you should write it out. But for me, this is probably fine. Okay. It's a bit of an art. I know it feels a little uneasy because you feel like, okay, mathematics, everything needs to be pinned down. But it's a bit of an art to decide what it is your reader needs to see. Okay. So hopefully you're developing some sense of that now. Okay, excellent. So a nice argument, but now let me show you how easy it is then, once we have this, to prove the next major theorem, which is the Heine-Borel theorem. Your book doesn't use this terminology, but everybody these days knows this name. So now we can show, yes. Yeah, so the question was, why are we using open sets to consider for covers? Why would it ever be interesting to look at closed covers? And the answer is actually coming in a couple of theorems when we talk about Cantor's intersection theorem. So you can develop the whole theory of compactness using just closed sets. But then instead of unions that cover, you're going to be talking about intersections that are finite. But perhaps you're asking a deeper question, which is why open covers at all, right? And that's a harder question to answer. So we'll be talking about. Well, so let me come back to that when we do Cantor's intersection theorem. Okay, so now we can show the Heine-Borel theorem. Which basically characterizes which sets are in R or in Rk, if you have k-dimensional k-tuples, k-dimensional space, Euclidean space, which sets are compact. So in R or Rk, K is compact if and only if K is both closed and bounded. Some of you guessed this theorem last time. I'm going to box this because it really is such a key theorem. And then we'll try to prove it. Oh, thank you. Yes, I should maybe say Rn. Yes, that it's not get K is unrelated to the other K. Thank you. Okay. Proof. Let's see. Which direction would you like to do first? Yeah, forward direction we've done already. We've both shown that a set is compact. If it's compact, it's closed. And if it's compact, it's bounded. Yes? In fact, we even reviewed the proof right at the beginning of class today. Okay, so what about the reverse direction? And here is a very, very important place to point out that the reverse direction is not true in arbitrary metric spaces. The question was, is the forward direction true in arbitrary metric spaces? And if you think back to the proof, the answer is yes. Those arguments we did with the pictures, and we drew balls. There was nothing special about it being RK, a Euclidean space. So forward direction is always true. The backward direction is not true in arbitrary metric spaces. And I challenge you to think of some examples before we finish this proof. Okay? And then we'll say some examples. Okay, great. So, how do we show that if it's closed and bounded, it must be compact? Well, check this out. This is so cool, this proof. Look, K is bounded implies, if K is bounded, what does that mean? Well, that means K lives in some what? in some ball, and we're just going to do intervals, but if you want to do Rn, you could do K cells or whatever, right? Would you agree that K lives in some interval? An interval sufficiently big enough, right? Maybe from minus R to R for some R, would you agree? And if it lives in open minus R to R, wouldn't you agree it also lives in closed minus R to R? That's what it means to be bounded. Would you agree this is a consequence of being bounded? Yes? Oh, great. But what is minus R to R? It's an interval. It's a closed interval that therefore is what? Compact. Excellent. So you have a compact set, and K is a closed subset of a compact set, and therefore K is compact. Nice. Lots of, that was very easy. But K is compact, and this minus R to R, sorry, K is closed because it's, that was the assumption. Minus R to R is compact by the previous theorem. So K is compact also by a theorem. End of story. So showing this for closed intervals being compact was essential. I mean, was basically we did a lot of hard work there, and now we're just reaping the benefits. Okay. So any subset of R that's closed and bound is compact. Now, what would change if I were doing this in Rn? We just have to show that a K cell is in fact compact, which the same argument would also work, right? Instead of intervals, we'd have boxes that you would do what? Subdivide the boxes into tinier boxes, yes? Okay. And you want to prove a nested interval theorem, nested box theorem for RK, which would follow pretty much the same proof as up here for nested intervals. Okay? Emil. The product of you could show the product of compact sets is compact. There's some work involved there as well, right? Yeah, I wouldn't say that it's I wouldn't say that it's an easier approach, but it's certainly true. The product of a pair of compact sets is compact. It's not true for, well, product of pair of compact sets is compact. Okay, and I can't even say what it means to be true for arbitrary products until we define what the open sets are for the arbitrary product. Okay, and for a particular choice, it'll be true for arbitrary products as well, and that's known as Tikhonov's theorem. Yes. Ooh, you guys are asking great questions. Okay, before I answer that, let me just write this down here because I want to make sure it's in your notes as well. So for RK, replace the interval by a K cell. Okay, so your question was, where does this break down if R has some other metric or some other notion of distance? Excellent question. So is it the case that AB is compact with another metric? Certainly this argument rests on the fact that this interval is compact, right? So now let's look at this interval. Suppose I give it the discrete metric. Discrete metric says distance is 0 if they're the same point, and 1 if they're not. Is that compact for an infinite set? In fact, an uncountably infinite set? No, it's not compact. Why is that? Because you could cover every point with a ball radius 1/2. That's an open cover where every point is precisely one element of the cover. So you can't remove any of them and still be a cover. So that under the discrete metric is not compact. So then maybe you're asking, where does this proof break down? Well, if this were the discrete metric, then you're resting on the nested interval theorem, right? Right. Where does this break down? Certainly, at least one of the halves has no finite subcover. Yes, this is where it breaks down. So x is a point, right? And what does it mean to be in some set of the cover, whatever it is? Well, it's interior, but the interior of such a point is not actually an interval for a discrete metric. That's right. So this point would be, it's an interior point, but the only thing in that interior set is just a single point. And so you'd never be able to have the contradiction that the cover necessarily covers one of these blue things, which is where the contradiction came. Excellent question. Love those questions. Keep them coming, even though it forces me to think on the spot as well. Okay, any other questions about the Heine-Borel theorem? Now that we've discussed this, can you think of an example where the reverse implication is not true? Give me a metric space where the reverse implication is not true. Closed and bounded, but not compact. Discrete metric on a infinite set. Yeah, discrete metric on an infinite set. So, example, let's take a discrete metric on an infinite set. The entire space is compact. The entire space, let's call this infinite set A. Well, then A is compact, is closed. Why is it closed? It contains all its limit points, which namely are, if it's discrete, does it have any limit points? No, because everything can be separated by these isolated balls. So it's definitely closed. Is it bounded? If all distances between points that are different are 1. Is it bounded? Yes, everything's in a ball of radius 2 around any of the points. Good. But is it compact? No, because you can't remove any element of the cover if the cover is balls of size 1/2. Okay. On your homework, you're going to explore other examples. Another example. Let me give you a related example, because I want to begin to have you thinking about metric spaces that are not just R or Rn. So here's another example. We don't yet even know what these words mean, but assume, based on your calculus understanding that you do, you know what the word continuous means, but that's coming up in several lectures. Remember, you could put a metric on a function space. Let's say C of R is the set of all continuous functions, f from R to R, where this R represents the domain. Okay. Continuous functions on R is the way we read it. And let's make the metric between any 2 points just the suprema metric, which is the distance between f and g for all x in R. Oh, and I probably should make sure that this distance is always defined. It might not be if this soup gets too big. So let's just make sure, let's just say that these are all, let's say these are bounded functions. So the little b refers to bounded functions on R. Okay, so the distance between any two functions is the maximum or the supremum of the. It's basically the biggest distance it achieves or approaches. Okay. So here's a question for you: what's the neighborhood around a particular function going to look like? This is kind of fun, actually. Give me an epsilon ball around f. What is an epsilon ball around F going to look like? Willie? If you did what? Yeah, if you did the function in bold, if you put a little ribbon around this function, it's any other function that lives in a ribbon. Sorry, I'm going to stop dotting, but I'll just put a little ribbon. And Willie said, think about it in bold. If I put a little ribbon around this, to be in an epsilon neighborhood around F is any other continuous function that lives in this ribbon. Are you with me? That's what it means. That's what an epsilon neighborhood is. Yes? Oh, excellent. So you could imagine, you could talk about covers of sets, right? An open set of functions is basically a function, a set of functions, such that for any function in that set, you can perturb it a little bit and it's still in that set. Perturb it within a ribbon. Yes? Oh, okay. So function spaces they're infinite dimensional spaces. They're kind of weird, and you can certainly construct examples of sets that are closed and bounded but not compact. Here's an example. Yeah. Yes. So G is not in this particular epsilon neighborhood. It might be in a bigger neighborhood. It's not in this one. Okay, excellent question. So let me show you a set that is closed and bounded but not compact. Here's one. Here's a set of functions. Let's take a function that has a spike at, I don't care, how about the point n, and let's call this function fn. And let's say we're going to limit ourselves so that it lies between n plus a half and n minus a half is the only places where it's non-zero. So suppose I look at all such functions. Would you agree they're just a bunch of spikes like this, yes? Etc.? Yes? Let's look at this set. Let's call this set A, which is the set of all Fn for n and z. I claim this set is closed. Why? Take a little ribbon around this set, around one of these functions. If you take a ribbon around one of these functions of size, let's say, I don't know, something small, less than a half, would you agree that none of the other functions live inside it, that ribbon, a tiny ribbon? Oh, so this set has no limit points. So it's closed. It's infinite also, yes? Is it bounded? Well, what's the distance between any two functions? At most 1. Oh, so it's bounded, it's closed. In fact, the topology, if I can use that word, induced by this suprema metric on this set looks just like the discrete metric, doesn't it? So if you wanted to cover it with an open cover that has no finite subcover, take little ribbons. That's an open cover of this set that with no finite subcover. Okay, good. So hopefully I've convinced you this is not an arbitrary fact, but it is a fact about Rn. All right, let's take a couple-minute break, and after the break, I want to prove a couple more important theorems about compactness. Okay, let's resume. Let's resume. So before the break, we proved some facts about compactness. In particular, the intervals or k-cells are compact. And something more generally, a set is compact in Rn if and only if it's closed and bounded. Here's another characterization of compactness that is true in arbitrary metric spaces. unlike the other characterization, which is only true in Rn. K is compact if and only if, I claim, every infinite subset of K has a limit point in K. So this is a crucial fact about compact sets. Every infinite subset of K has a limit point in K. So if you think of compactness as a small set, a compact set being small, does this characterization kind of make sense? That is, if you have an infinite subset of this thing, and it's small enough, then all those points should do what? Here's something that's kind of a small set, and you have infinitely many points, then what should be true? If you try to pack a large number of points in a small space, the points should what? They should accumulate somewhere, right? They should have a limit point. Does everybody sort of see the intuition? Okay. Okay, so that's basically the idea. So let's see if we can prove this. Proof. Let's do the forward direction. What would go wrong if there was an infinite subset that had no limit point? What would go wrong with the fact that it's compact? Let's see. Let's draw an alternate picture. Here's another picture. And now you have infinite subsets, a subset that has no limit point. So what does that mean about each of these particular points? They're sort of spaced out in some way. Why? How does that what does that have to do with being a limit point or not being a limit point? Good. If this is not a limit, if this point is not a limit point, you could find a ball around it, yeah? And you could find a ball around this one. You could find a ball around this one that doesn't, they might overlap each other, but they don't overlap the other points because this is not a limit point of any of the other points. Agreed? So that's the picture to look at. So we're doing this by contradiction. If no point, if K has no limit points, has a limit point in K. If no point of K is a limit point of our set, can I give the set a name? Let's call the subset E. I'll call this subset E. If no point of K is a limit point of E, then each point Q in K has a ball around it, has a neighborhood, let's call it VQ, that contains, you can make it small enough to contain at most one point of containing exactly 1 point of K. The point Q of K. Or maybe another way to say it is containing no other point of K other than Q. That's what it means to not be a limit point. If no point is a limit point, then each Q has a neighborhood. Oh, but this is a cover. VQ cover E with no finite subcover. I'm going to abbreviate this. No finite subcover. Question? Yes? If every K is compact, if and only if every infinite subset of K, if and only if every infinite subset E of K has a yeah, sorry. Let me just think here. So we have some subset. The set E are these infinite things. The set K is the entire big set. And the claim is that K is compact if and only if, no matter which infinite subset you pick, then it doesn't have a limit point. Every infinite subset has a limit point that's actually in K. So the statement is correct. Oh, yes. Okay, thank you. If no point of E, no. Yeah. The limit point here is a limit point of E in K.
Q and E to have neighborhoods containing exactly 1 point of E.
Ah, thank you. Yes. Right, which is what my picture suggests, but I just didn't draw. Containing exactly 1 point of E. Thank you very much. Good. Thank you. Excellent. Okay, so in the forward direction, what I've shown is K can't be compact because this is a cover with no finite subcover. So K, if this is not true, then K is not compact, and that establishes the forward direction. All right, what about the reverse direction? The reverse direction assumes that every infinite subset has of E has a limit point in the set K. And I'll just say that the reverse direction is actually a lot harder to show for arbitrary metric spaces. And the proof for arbitrary metric spaces is a hard homework exercise, okay? Which may be assigned because they're hints. But I'm going to do the reverse direction for RK, even though it's true more generally. It's easier to get a sense of why it's true. So here, this proof is for RK, or Rn if you like, but it is true for all metric spaces. Okay, so if I want to show this is true for RK, for Rn, and I want to show that now that K is compact if it has this property, what other theorem might be helpful if I'm showing something is compact in Rn? Yeah, Keith is thinking Heine-Borel would help a lot here, right? Okay, so we'll show K is closed and bounded. All right. So that's not bad. Suppose K isn't bounded. And I'm going to just sketch this idea here. Suppose K is not bounded. What would that mean if K is not bounded? Why would that contradict the fact that every infinite subset has a limit point if K isn't bounded? It goes off forever. Here's some set K. Not bounded. Not bounded. You're trying to do this by contradiction. You assume that we're assuming every infinite subset has a limit point. Why is it the case if K were not bounded that might contradict that statement? Every infinite subset has a limit point. Can you think of an infinite subset that would not necessarily have a limit point in this picture that goes off forever? Can you think of a subset? Well, does this picture suggest one? Yeah, how about some set that just keeps going off forever? I don't know why I'm yelling like that. Okay, but let's see. How can I make this precise? Would you agree this is an infinite subset that has no limit point? Why does it not have a limit point the way I've drawn it? Because I can surround it by balls that all only cover exactly one point, something like that, yes? Okay, this is the idea. How do I say this? Well, if k is not bounded, then we're just going to choose a sequence such that the absolute value of the nth point is bigger than n. How's that? Are you happy with that? This is in Rn, you can make the distance from the origin be bigger than n. Yes? So all these points are like points that are on one side of, this is distance 2, this is distance 3, this is distance 4, distance 5, distance 6 from the origin. Yes? Now I know what you're thinking. You're saying, well, wait a minute. Maybe the point you pick beyond 3 is actually like, close to the 4th point, right? Or maybe the points 5 and 6 are actually close to the 7th point. Why is that not a problem with this argument? Yeah, this thing's not going to have a limit point clearly, because if it did, that point would have to be somewhere, yes? Maybe between the millionth and 1,000,000,001th radius. But what did we show? Why can't that be a limit point? Because in the neighborhood of a limit point, you must have what? Infinitely many points, and you only have finitely many that are to the left of 1,000,001, right? That's the argument. So this is these have no limit point. And I'm just going to let you. I just said the argument. I'll let you check that for yourself. Okay. The neighborhood of a limit point must have infinitely many points of the set, but any point here has only finitely many points that could be near it. Okay, good. So that shows that k is bounded. Suppose k is not, suppose you want to show it's closed. If it's not closed, how can we get a contradiction in this situation? So this picture is like this. Here's k, and it's not closed. Okay, whatever edge means, but you just mean take a limit point that's not in set, that's not in k, yes? Yes? But then any neighborhood around it has a what? A point of k in it, yes? So pick one. And now what? How do I get like a whole bunch of points that accumulate on P? Good. Keep taking smaller and smaller radii that go the radii go to 0, and pick points inside. So if k is not closed, there exists a P not in k that is a limit point of V. And now choose xn such that the distance from xn to z is less than 1 over n. That would do. And this set xn has no limit point. Has a limit point at P. And what's the other thing you'd have to show? Not only does it have a limit point at P, but you're trying to show this has no limit point in E. Why does this have no limit point in E? Is it possible for it to have a limit point that's P, but also maybe something else? Hopefully not, right? Can you see why that's the case? Why must do these points, the way I've constructed them, only have one limit point? Well, if it had 2 limit points, those limit points would have some distance between them. And then it cannot be the case that this sequence is getting closer to 1 and the other at the same time, because at some point the triangle inequality would break. Right? That's the idea. Has a limit P and no other. I'll leave it at that. But this is a sketch of a proof see, we drew a couple of sketches. See, sketch. But you obviously would want to justify this more carefully. Okay? Okay. But the important thing here is sort of to get the idea. All right. This has a very, very simple corollary, and that corollary is the following, which is sometimes known as the Bolzano-Weierstrass theorem. Some of you have seen Bolzano-Weierstrass before, which basically says that every bounded subset of Rn has a limit point. Clearly, I mean in Rn as well. Now, why is this a corollary? Is Rn compact? No, not compact. So I can't just apply this theorem. I claim that every bounded subset, infinite, better be infinite, which I think is maybe what Jenny was going to suggest. Yes, that's right. Thanks. It should be infinite subset. So Rn is not compact, but what? You give me a bounded subset that lives in a compact K-cell, right? So the boundedness gives you what you need. So proof, if the subset E is bounded, then E is in some compact K-cell. And therefore, what? It's an infinite subset of a compact set, and therefore it has a limit point. So it has a limit point by the previous theorem. It's a bounded subset of a compact set, so it has a limit point in the K-cell. Okay, another big theorem that wasn't too bad to show once you develop some machinery. Okay, and we did the forward direction. We used the forward no, we used the backward direction. Okay, so for an arbitrary, for Rn, we've shown it. Okay, and it's true in general, and that's in one of the exercises. All right, let me finish with another characterization of compactness. And this is a theorem due to Cantor. And it's sometimes you refer to as the finite intersection property. So suppose you have a bunch of sets, K alpha, and they're compact subsets of some metric space, some arbitrary metric space X. It's a collection of compact subsets. Here's a theorem. The theorem says if any finite subcollection has, okay, so this is a bunch of sets, but if you take any finite number of them and you intersect them, if those are all non-empty, those intersections, then in fact the entire collection has non-empty intersection. So if any finite subcollection has non-empty intersection, then the intersection of all of them is not empty. You should see this theorem as a generalization of what theorem you've seen before. Nested interval theorem. Closed intervals are compact. isn't it true for nested intervals? If you take any collection of finitely many of them, their intersection is clearly not empty because it's just the smallest one, right? And the conclusion there was there's a point in all of them. That's the conclusion here. Okay? So this generalizes nested interval theorem. And it's true for arbitrary metric spaces, not just intervals in Rn. Okay, let's see what the proof is. Proof is actually not too bad. And I claim, this is a statement about compact sets, right? Compact sets are closed. So their complements are open. So this is really a statement about open sets. Let's let U alpha be the complement of K alpha. And these are open. Okay? Now, if this intersection of the K alphas were empty, I claim their complements would cover everything. Because if a point is in the intersection, that means that point is not in any of the complements, right? So if there's no point in any intersection, then every point must be in some complement, which is in one of these things. So this is the key insight. I'm going to fix, if you don't mind, some k in K alpha. I'm going to pick my favorite compact set. I don't care which one. Fix one. I'll call it K. Okay. Now, the thing to notice is if the intersection of K alpha over alpha were empty, then the U alpha, I claim, cover that one particular set. If the intersections were empty, then this thing would cover not only the whole space, but this set, which we know to be compact. Okay. But what does that mean? That means there exists a finite what? Subcover. I might as well call it U alpha sub 1 through U alpha sub n, covering K. Yes? Oh, but what does that mean? Well, I claim that means if these things all cover K, that means K's intersection with their complements, K intersection K alpha 1 intersect K alpha n, must be empty, which is contradicts the hypothesis. So this is a proof by contradiction. So by contradiction, for the sake of contradiction, we assumed if this were empty, we get this statement, which is a contradiction, contradicting the hypothesis. So what we have here is basically another way to think about compactness in terms of a finite intersection property instead of a union of open sets which cover a compact set. Here we have basically a bunch of compact sets which have a finite intersection property, then their entire intersection must be non-empty. Okay. A classic example of this is something called the Cantor set, which we will talk about a little more next time. Okay.